Maths educational video, higher order partial derivatives. What we are going to do in this video is to differentiate the first order partial derivatives of a function of two variables, say x and y, with respect to x and y again. It makes sense to do this because these two first order partial derivatives are themselves functions of x and y. And differentiating them will produce what we call second order partial derivatives. Obviously, there are four of them. If you differentiate the partial derivative of f with respect to x one more time with respect to x, you will get d squared f dx squared. If you do it with respect to y, you will get d squared f over dy dx. Exercise caution when you write dy dx. Over here, it's understood that you do x first, then y. However, if you write in the other way, then fxy means you differentiate with respect to x, then followed by y. If you find these notations cumbersome, my advice is to write in the most unambiguous way. Simply write d over dy of df dx. Writing this creates no confusion because we know that we are differentiating df dx with respect to y. So we can define second order derivatives by differentiating f subscript y with respect to x or y in a similar way. Let's look at one example. Here the function f is a composite function, cosine of 2x plus y squared. Our job is to find all the second order partial derivatives. So obviously we have to first find the first order partial derivatives. Let's first work on fx. We differentiate cosine 2x plus y squared with respect to x. Applying the chain rule, cosine will give minus sign. Of the same angle, 2x plus y squared will remain unchanged, followed by the differentiation of the term inside the bracket, which is 2x plus y squared. Because we are doing with respect to x, y is treated as a constant. So differentiating y squared will give us 0, and differentiating 2x will give 2. So we have obtained f subscript x. We will now differentiate this function first with respect to x, and then with respect to y, to get the second order partial derivatives. Now we work on f subscript y. Again, applying the chain rule, we will get minus 2y sine 2x plus y squared. Now we differentiate this function with respect to x, and using the chain rule, we can get this answer. Just a word of caution. In this expression, minus 2y is a multiplicative constant. It's a constant because we are doing differentiation with respect to x. And finally, for fyy, more work has to be done. And that's because, according to the two terms I have highlighted, one in green and one in orange, both involve y. So it's time to use what is known as the product rule. According to the product rule, we will first differentiate the one in green with respect to y. That will give us minus 2, and we will copy down the other term in orange. Next, we will differentiate the one in orange with respect to y, and copy down the one in green. An important observation. In this example, fyx equals fxy. Both equals to this expression that we have just found. One natural question to ask is this a coincidence or is something true in general? The good news is, in general, when f satisfies certain conditions which are not too stringent, these two derivatives, sometimes known as mixed partial derivatives, are equal. The condition we require on f is that these two mixed derivatives are continuous functions. We will not go deeply into the concept of continuity for functions of two variables. All I can say is most functions we encountered in real applications will enjoy the above property, so we shall take this for granted. Let's end this video with two important remarks. First, it's possible to define partial derivatives of order 3 and above in the most natural way. All you have to do is to keep differentiating. For example, if you want fxyy, then essentially you will differentiate f first with respect to x and then with respect to y 2 more times. In other words, you will first find the second order derivative d squared f dy dx and then differentiate this with respect to y to get the desired term. We can also define high order derivatives for functions involving 3 or more variables, again in a natural way. So here is a quick example to illustrate this.